You guys hear me now? Okay, sounds good. So my talk is called From Silicon to Compiler, and it's pretty much that. So we're going to start off with what we're doing, why we're doing this, then a little bit of architectural background on programmable logic for those of you who have not done work on programmable logic before. Then jump to a block diagram of the device. We'll start with a high-level overview of the silicon, and then we'll drill down into more interesting stuff, down to transistor level and gate level circuit analysis. At the end, I do have a live demo of firmware produced by my tools running on live silicon. Sadly, there are no cute cat pictures in this presentation. Sorry. So a little background about me. I pretty much like to build and break everything. I will do web stuff if they pay me enough. I mostly like to live down in low level, a bit of Ring 0, firmware, low-level board design, RTL design, and now getting down into the transistor level. I just finished up my PhD a few weeks ago. During that time, I designed and created what I believe is the first ever college class on semiconductor reverse engineering. I tried quite hard to find another one that I could borrow notes and slides from. As far as I can tell, none existed. I'm also obviously a significant contributor to Silicon Prawn, so if you see all the guys walking around with decap chips in their shirts, say hi. I've only been with IOActive since January. A lot of this work was actually done before I joined the company, but they've supported me continuing the work, so I acknowledge them for that, obviously. So as far as what we're actually trying to do and why, programmable logic is really everywhere these days. You may not know it, but a lot of, especially high-end networking, AV, all sorts of stuff has programmable logic in it. Because ASICs these days, the tape-out costs are so high, especially for leading-edge process nodes, it usually is not actually cost-effective to make custom silicon unless you're making a huge number of them, like for a smartphone or something. For anything else, you're probably better off running on an FPGA. And the problem is they're full of black boxes. Nobody really knows what happens when you compile your bit stream onto a device. You know, okay, well, we've got these lookup tables, we've got these RAM blocks, but what is actually going on underneath? How do I know that the RTL I gave the compiler is actually equivalent to what the actual device's behavior is? We don't know. Or how do I do development on a platform that is not x86 or x64 or Windows, or one of a very short list of Linux distros they support? Sorry, out of luck. And let's say we think we found a compiler bug. Oh, we just pop the code and objdump and look at it. Nope, there is no decompiler for the bit streams. So if you think it's generating bad code, sorry, you're screwed. And of course, reverse engineering, this is REcon. The vendors want people to think bitstream reversing is hard. They advertise their closed source proprietary format as being impossible to reverse engineer. It's not. So as far as the methodology here, I just decided earlier today to take a look at the size of the directory I had installed the Xilinx tools in. 18 gigabytes. I don't know about you, but I don't have time to look through 18 gigabytes of stuff in IDA. There are much better things I could spend my time on. And plus, the license agreement says I'm not supposed to be reverse engineering their software. I never agreed not to look at the silicon. So open source by any means necessary. So this is our target. It is the Xilinx XC2C32A. I chose it for a bunch of reasons. One is that it is very cheap. They're about $1.15 each on DigiKey in single units. As of a couple of weeks ago, I think the price just went up to $1.20 something. But they're still cheap enough you can afford to kill large numbers of them testing. You have your choice of a nice big QFP package that's easy to hand solder, has plenty of plastic around the package so it's easy to decap while keeping bond wires intact. Or you can do chip-scale BGA or QFN if you just want to dunk the thing in acid and get rid of all the plastic and take a look at the silicon. It's a nice, friendly 180-nanometer process, 4-metal UMC, so you can actually read out most of the upper metal layers optically. You don't have to bother going into the electron microscope except for the lowest layers. So that helps. It's a lot easier to use an optical microscope than a SEM. It's a lot quicker to shoot a lot of images quickly. The bit stream is also not that big. It's around 12K, so there's not really that much there to reverse. And it's also a fairly simple architecture. You're not going to find block RAMs and embedded ARM cores and all kinds of stuff like that. It's just pure programmable logic. And the vendor tools are free, which always helps. Hackers are cheap. So the bitstream format for this thing at a high level, the output of the compiler is a JEDEC programming file. It's basically the equivalent of IHEX, but instead of being hex lines, it's binary lines, ASCII ones and zeros. So This is the exact data that gets written to the chip, not in the actual order. I'll get to that later, but there is a one-to-one correspondence between these ones and zeros and the configuration bits on the device. And the nice thing is that, as you can see on the right side here, the bit stream generated by the Xilinx tools, if you're so inclined, does have comments. Turns out they're not very useful. They just say, okay, block 0 ZIA. Well, what is a ZIA? Look in the data sheet. There is not one reference to ZIA. Okay, doesn't really help me much. So let's get a little bit into the architecture of what a CPLD actually is. So any digital equations can be expressed using a form known as sum of products. It's a canonical representation of digital equations in which you take a series of terms, you bitwise AND them together, either the input or its complement. You can just treat the complement as coming into your device. So you've got A and B and C, or C and D and E, etc. So you can express any arbitrary digital equation this way. So let's look at how we'll actually make a chip to do this. So if we have a large, say, 32 input AND gate, and we have a mux the input to each gate, or at each input to the gate, that lets me select between a constant 1 or the input to my circuit. I can effectively mux any subset of these inputs and just leave the others as 1, which is the identity for the bitwise AND operation. So I can AND together any subset of the possible inputs to this AND gate. The same thing can be done for OR. Obviously, you have to use 0 as the identity element for bitwise OR. But what this means is you can create a gate that has a huge number of inputs, and I can pick any subset from those at runtime with mux settings. So this leads to a natural structure for a programmable logic device. You make a grid of gates with a 2-to-1 mux at each input. You've got inputs coming in, outputs going down, and then you just have a series of gates in sequence ANDing stuff together. So this is actually a render from my tool. You can see we've got the input coming in. We select either X or X prime, and that with the data coming in from overhead. Take the output of that. Now here we skip the AND gate. This is more of a logical view, so I'm not actually showing the actual muxes in the chip. This is more of a schematic view of what the circuit logically does. I'm also rendering it as a cascaded sequence of gates end to end. In practice, the actual implementation on silicon is usually a tree because nobody wants order n propagation delay when you could have order log n instead. So if we take this and we want to build a full programmable logic device, what we do is we take a bunch of signals coming from our registers that store state. We take a bunch of signals from our input pins. Then we feed these into an AND array. We invert them, so we have 2 times however many inputs. We take M product terms out of that. The product terms then go into a programmable OR array. The output of that gives us, we'll just call it R outputs. Then we feed those either into an output pin or into a flip-flop if we want to do state machines or something like that. So this is really all it takes to build a simple programmable logic device, or SPLD. The problem is SPLDs scale poorly. You end up having quadratic scaling with the number of inputs. Nobody wants a die whose size scales quadratically with the amount of work it can do. That's terrible. So how can we improve this? Well, it turns out we can make a grid of small SPLDs. Did not show up as well as I had hoped on the projector, but we've got one SPLD block here, we've got one here, and there's a crossbar switch in the middle. So now we can create a bunch of outputs from one SPLD, a bunch of outputs from the other, and then just feed them all into one big routing fabric, pick out whichever signals I'm interested in processing on this half of the chip or that half of the chip, and then feed them into the SPLD. So this is a CPLD. So now let's look at the specific CPLD that we've been targeting today. So there are 32 GPIO pins, which are full input-output, plus one input-only pin. I'm pretty sure this is because they intended to package the die in a 44-pin QFP package. All of the other stuff for JTAG, power, and the 32 GPIOs use 43 pins. They didn't want to have one NC pin, so they just threw one extra signal into the global routing that you can't drive, and it just serves as an extra input. And then the remainder of the device is 2 function blocks, which are basically SPLDs. Each one has 16 GPIO pins, 16 flip-flops. Of the 65 signals in the global routing, so 32 IOs, 32 flip-flops, plus one input only is 65. We pick 40 of those, feed those into an 80 by 56 AND array, then a 56 by 16 OR array. This is all documented in the datasheet. What's not documented is, okay, we can make a technology mapped netlist. We know, okay, I have these inputs ANDed together, these outputs ORed together. Now, how do I actually make the chip do what I want? So, time to put in our lab codes. I am not going to talk about decapping and imaging. This has been beaten to death in other talks like REcon last year and I think the year before that and probably the year before that. So we're not going to cover that. There's a lot of good stuff up on Silicon Prawn. There's, if you read the lecture notes from the class I taught at RPI last year, there's a lot of good material there. But this talk is about reverse engineering, not on sample preparation. We're not going to be teaching you how IDA works. We're teaching you how to actually reverse engineer this specific device. So here is the Metal 4 overview of the device. We can see that there is a roughly left-right symmetry. It's not exact. You can see here there's something that's not mirrored here, but up here it looks like the device is pretty symmetrical. So first impression, we've probably got the two function blocks left-right symmetric on the device. Let's go down a little bit. After we've etched off all of the metal and poly layers, we're now looking at the implant layer. This is after a process known as dash etch, which stains p-type doping either brown or it shows up raised under the electron microscope. Mainly, though, it's useful because it provides contrast in areas of gates. So you can see we've got pairwise symmetry here and here. Those are probably the function blocks. There's something down the middle. That's probably the global routing. Then there's a large memory right here. Pretty obviously the EEPROM where the bit stream is stored. Then if we actually follow the bond wires from the die out to the pins in the package, you can see these are the JTAG pins, TDI, TMS, TCK, I believe top to bottom. The TDL pin is right there. So we can conclude that the JTAG shift register probably runs left to right across this configuration area and somehow allows you to write to this EEPROM here. There's also a few smaller pads. There's one up there. There's one up there. I think there's one on the upper left. There's a total of 6. I have not yet figured out what these do. It wasn't necessary to reverse the portions of the device I needed, so that remains future work. So let's take a closer look at the function block. So we know there are 16 macrocells. Each macrocell contains one flip-flop and stores the output of one term of the OR array and has a little bit more glue logic I'm going to talk about later on. So there is 16 wide symmetry here, 16 identical copies of this. Just by looking at this, we can be pretty sure we're looking at the macrocells. Then we see some structures up here and here. This looks symmetric, this looks symmetric. This looks symmetric but different. So as it turns out, the AND array is not actually one solid block. The AND array is split in half. They've got 20 signals here, 20 signals here. Collectively, that forms 40. Then they AND the outputs of those two individual blocks together. That gives you our product terms, and then that goes into the OR array here and then out the macrocells. So now let's take a quick look at the configuration bit structure before we dive into detailed die analysis. So the programming documentation does talk a little bit about how the device is put together. It turns out that even though the JED format is supposed to be something you can actually just feed to an EEPROM program and load the device, that's not the case here. The bit ordering in the JED file is actually virtual addressing in which they abstract away all of the quirks of the silicon. So, for example, all of the AND array bits and all of the OR array bits are in the same order in the JED file for each one. Turns out half the actual AND and OR array blocks on the device are mirrored left-right. So you actually have to do address translation before you can take a bit stream generated by their tools and flash it to the chip. Luckily, they do sort of document this. There's a big Excel file they publish to people who are making programming adapters that is just a big grid of output and input and just has an entry at each cell. It says, okay, which config bit from the JED file goes to this physical address? So it doesn't really tell you much about how the chip is put together. The actual structure is 48 rows by 260 columns. There's one extra row full of configuration metadata. I'll get to that later. But it stores 7 lock bits, which some of them are always 1. I'm not entirely sure what purpose they serve. The remainder are 1 for an unlocked device and 0 for a locked device. Then there's 2 done bits, which indicate, okay, this bit stream is valid. We have a legal firmware image. The chip has been fully flashed. And it turns out also only 258 of the 260 columns are usable. The remainder are what we call transfer bits, which, as far as I can tell, you just put them as a constant 0. It just indicates, hey, this row of EEPROM has actually been programmed. We didn't abort halfway through programming. There is some documentation of this in a patent from Xilinx, but it didn't really give enough detail for me to figure out, okay, why are they doing this? And the other intuition we can get from this is that since it is EEPROM-based, then FF is going to be the state of the memory when the chip is blank. So therefore, we expect most of the memory on the device is going to be active low. So most things should be turned off when the bit is high and on when the bit is low. We just don't know exactly what that bit does yet. So now let's take a look at the actual die structure. So you can see that the configuration memory is not actually one block. We've got an array here, one here, one here, one here, and one hiding all the way over here. And as it turns out, The sizes of these are symmetric about the center, and they go directly up to the corresponding logic. So it's pretty obvious we found the memory that configures that part of the chip. The data just flows straight up during the boot process. So this configures the end in the OR array, this configures the global routing, this configures these macrocells, this configures these macrocells. We can confirm this if we look up at the metal 2. You can actually see the lines coming off the sense amplifiers for the EEPROM going up and vertically into the array, and if you trace it out all the way, you can actually see it writing to the individual configuration SRAM cells in the die. There are a few bit lines here and here, for example, that are connected in, I believe, metal 3 instead of metal 2. They couldn't fan it all out in one layer. So now let's take a look at the main logic array. If we actually look at where the SRAM cells are and count how many rows high each individual block are, we see that the AND array is 20 rows high, the OR array is 8 rows high, other half is 20 rows high, and each macrocell is 3 rows high. So that gives us a pretty good idea. We know left, right, which bits in the bit stream configure which logic just by what's physically proximate to it. And we can make a pretty good guess that since we have a 2D SRAM array here in the configuration area, we have a 2D flash array, we probably have either top to bottom or bottom up addressing. There's actually some gray code going on. It's a little more complex than that, but logically, we should have the addressing going across vertically. So if we take a closer look at the AND array, we know that there are 56 product terms. We know that there are supposed to be 40 rows and 40 complemented rows for a total of 80. If we actually count how many SRAM cells are, we'll see there's 112 bits wide, which is 56 times 2. There's 2 blocks of 20 rows each. So the conclusion is that since we know there's 40 inputs coming in from the crossbar, we've got 2 blocks that are each 20 rows high. Each row probably corresponds to 1 row of input. And then we know that the width of the array is double 56. So there's probably 2 bits per product term. One selects X, one selects not X, or maybe some sort of other code. As it turns out, it is one hot coded. I just figured this out by experiment. It was pretty easy. Just try one, see if it works. If not, try something else. There's only 4 possibilities. So the OR array turns out to be 56 AND terms, 16 outputs. If we count the config bits, it's still 112 bits wide. It's the same, coming up off the same EEPROM, but it's only 8 rows high. And there's only 56 inputs. Since the OR array does not have an X and X prime input, my conclusion is that we still have one hot selecting for one particular input, but we do have 2 actual arrays of the OR array interleaved in one configuration row. Again, a little tinkering was pretty simple to figure out the actual bit ordering. So now let's take a look at the macrocells. There are 27 configuration bits per macrocell. If we look, you can see there's 160 SRAM cell, 160 SRAM cell, and so on. There's a 9x3 grid. It turns out this 9x3 grid does not actually control one macrocell. The bottom 2 rows of this RAM control the bottom one. This goes to the upper one. This threw me off a little bit when I started looking at the circuit, but it turns out that, yes, it is 27 cells. Yes, it is 9x3. No, the 9x3 structures in the die do not actually correspond to this. So this makes intuitive sense. The EEPROM at the bottom of the die is, well, okay, it's 10 bits wide, but we know one of them is a transfer bit. So the other 9 bits go directly up to here. I've figured out a significant fraction of the functionality, not quite all. There's still some clocking stuff I'm a little unsure on right now. These also configure I/O buffering and stuff like that. So there are lines coming out from these to the side of the device and controlling the I/O buffers. Now, I will, as a quick aside, jump into the security bits. We know there are 9 gun bits and lock bits somewhere on the device. We know that the physical address of these is in the right-hand macrocell memory. It's in the top row. There's 960 SRAM cells right here that don't appear to be hooked up to any of the actual logic array. I have not actually tried fibbing these. I don't know for certain that these are the lock bits, but it is pretty obvious. Especially when we know of those 9 bits, 4 of them have to be held low to lock the device. There's a 4-input NOR gate right here, and an inverter right there. I wonder what happens when I cut that line. I don't know. So now we'll get to the global routing. So we know between the left and the right halves of the AND array, there is something. We know that it is 20 configuration bits high for each half. We know it's 16 bits wide. We don't know anything more than that. The datasheet has about 2 sentences that talk about the global routing. So we have no idea whatsoever how it works. What we do know is that of those 65 signals coming in, we know that 20 of them go to the left function block, 20 go to the right. Those subsets may or may not have any relationship. And we know since it's 16 bits wide, we probably have 8 bits selecting what goes left and 8 bits selecting what goes right. So now here's the question. How do you make a 65 to 1 mux with 8 bits? If you just had 0 to 65, you'd only need 7 bits. If it was 1 hot, you'd need 65 bits. So what sort of strange, perverse code are they using here? The datasheet is of exactly no help. Well, time to get dirty. So if we jump into the electron microscope and take a look at the implant layer after dash etch, so you can see these areas here show up raised. Those are P-channel. These are N-channel. You can see that it's slightly lower. The raised areas are the individual channels of the FETs. This is zoomed out. The original image is a lot higher resolution, but I can't really fit it in the projector. So this is the implant layer. What we can see immediately is that there's some sort of symmetry going on, both horizontally and vertically. If we jump up to metal 4, we see that there are 6 small buses of 11 signals each. The rightmost is 10. All right? 5 times 11 plus 10, what's that, anybody? 65. There are 65 signals going into global routing. I think we found them. So I spent quite a while in Inkscape vectorizing this. My automated tools are not quite as well developed as I had hoped. So it did take me a while, but I do now have a full vectorization of the entire global routing matrix from implant layer all the way up to metal 4. The little gray boxes are not actual layout. They're standard cell outlines. So we've got a inverter here, another inverter here, another inverter here, and so on. So we can see that there are 6 identical blocks going left to right here. There's 2 weird blocks over there that are identical to each other at first glance, but not identical to the rest. Okay, this is starting to get interesting. So those big drivers on either side are pretty clearly the buffers driving the PLI. We've got a fan out of 112. We need a fairly big buffer. There is, I believe, 20-some fingers on this last inverter, so that looks like a high fan-out driver. It's actually a 3-stage inverter because the low-level stuff in the programmable logic doesn't actually have the drive current to drive that much gate capacitance. So they actually have a 3-stage driver inverting it again and increasing the current, inverting it again and increasing the current once again to actually drive the output. And of those 8 blocks, each one contains 2 SRAM cells. So it seems to make sense that we've got 8 blocks. We know that we have 8 bits controlling the left output. We have 8 bits controlling the right output. So we probably have 1 bit per block controlling what goes left and 1 bit controlling what goes right. Then there's 6 identical blocks, and there's 6 groups of wiring up in metal 4. So there's probably some sort of correspondence going on here. Again, we don't know what it is, but we know there's some relationship. So now let's take a look up at metal 3. So we can see there's power and ground routing here. We'll ignore all of that for now. But there are sets of 1, 2, 3, 4, 5, 6 vias per row. What's more interesting is there are always 6 vias per row, but they're not all in the same place. So there is, if we actually trace it out for all of the rows, each one of those vias is under each of the metal 4 groups. There is exactly 1 via in each row column intersection, but not at the same place. So now I finally realized what is going on. The routing matrix is not actually a full crossbar. It is a sparse crossbar in which, of the 40 rows, each row can only pick 6 of the 65 inputs. But there's a different subset for each one. And the end result is that using all of these subsets, you can select any unique subset of 40 of the 65. But you don't actually need a 40 by 65 crossbar. So now let's take a look at how the actual implementation works. We have a pretty good hunch as to how this is structured at a high level. We don't actually know what the implementation is. So I do apologize for some of the misalignment. This was a quick tracing, and so not all of the vias and metal layers line up exactly. This is not meant to be something you can clone the chip from. It's meant to be something I can figure out how it works from. So you can see there's a big pass transistor here. We've got the signal coming in from the upper layer here and here. And then we've got an output of the mux here. There's an SRAM cell that goes through a 2-input NOR gate and then drives that. So if we put this all together, what we see is that each row is indeed an 8-to-1 tri-state mux. So there's 1 pass transistor that selects each of the 6 possible outputs for a row. Then there's a single discrete NMOS and a single discrete PMOS that lets me drive constant 1 or constant 0 as well. It turns out that the driver for constant 1 is active high, all the rest are active low. So this means that a blank bit stream of FF won't cause bus fights. It'll put all the outputs in a well-defined state. So this makes sense. And all of the other signals are active low. There's also one additional signal I've called O gate. I have no idea exactly where it comes from, but I'm pretty sure that it's used during the boot process to basically pause the device, don't drive any of the outputs. It'll consume less power when the chip is idle. And it also prevents bus fights between drivers that aren't fully configured. If we've got half the device flashed and half not flashed during the boot process, we don't want to be driving signals onto nets that some other thing might still be driving with the old firmware. So as long as the signal is high, it gates all the outputs. And the rows are, again, not identical, but it turns out we can actually do the routing using MaxFlow. We just create a source node for each of the nets we want to route. We create a directed graph with paths for each of the legal connections to each row. Then we create a sync node with however many nets that we want to draw out, and we can just use MaxFlow to route everything. So as it turns out, the structure is pretty much that. I do have a full schematic. This is not it. I've kind of truncated the bottom to make it fit on the slides, but we've got a single configuration bit. We've got the NOR, which I've actually drawn as a negative logic AND, because that's really how it's functioning. Output of that goes to a single PMOS pulling high. We've got an NMOS pulling low. Then we've got mux in top A0, mux in top 90, and so on. Those are the actual hex codes for in the bit stream for selecting that particular input. So we'd make that row be set to A0 if we wanted to write to this element. And I do also have a table in the source for my tools that includes all of the mux settings for this device. So I now can fully control the global routing matrix. But there's one last bit. We know the ordering of the inputs. We know how to select one of the inputs and drive something. We don't know which input is actually hooked up to which signal on this bus. So, time to get dirty again. There were a couple of options I considered, but it turned out that one of the simplest was to make a few educated guesses about how things were structured. So, for example, all of the Macrocells in function block 1, their flip-flops are probably in a contiguous order in the bus. We don't know where in the bus they are, but they're probably contiguous. All of the input pins for function block 2 are probably contiguous as well. So let's tinker around a little bit. Okay, the inputs to function block 2 are probably contiguous. So there's not really that many orderings for the global input pin and these 4 sets of inputs. So let's just try tinkering and see which one works. So I went up to campus, hopped on the focused ion beam, drilled a few holes in the insulator over some wires, and laid down some nice, gigantic 20-micron square probe pads. And then I just started driving signals onto each net. Here's the code I'm using. It's just a counter going from a 2 megahertz input, dividing down to, I believe, a 2 hertz LED. And then I have one signal before that. So 4 hertz is on a specific flip-flop that I've constrained the tools. I'm like, okay, here, function block 2, Macrocell 5. So let's see. If we probe function block 2, Macrocell 5, or sorry, if we put a signal on function block 2, Macrocell 5 that's supposed to be 4 hertz, and we've got a probe pad on this signal, is it a 4 hertz square wave? Oh yeah, it is. All right, I guess it's right. So it didn't take too long to figure out the actual bit ordering. So here's the basic summary of the actual layout. We've got gates on metal 1 and poly. Metal 2 is vertical routing, SRAM bit lines, O-gate, then horizontal routing on M3, then M4 is the input bus. It turns out the actual ordering is the GPIOs for function block 1, the global input, GPIOs for function block 2, then the flip-flops left to right. So now we know pretty much enough to configure the PLA. Unfortunately, there's more to it, because it turns out all of the product terms, or nearly all of them, are dual purpose. They can be used as general purpose logic. You can feed them into the OR array. But each of the 16 macrocells also has 3 product terms that have separate dedicated connections to it. These are used for set, reset, clock, enable, and so on. I'll cover some of this in the next slide. 4 more have special connections to the entire function block, and the last 4, as far as I can tell from reading the datasheet, they have no special purpose. The datasheet does tell us these things exist. They tell us roughly what they do. They don't tell us which of these 56 product terms does what. So I will just briefly cover what these terms are. So we've got per function block, we have a local clock that we can use. So we don't want to waste global clock resources for the whole chip, but we also don't want to have a per flip-flop clock, because that'll both increase skew and use a lot of product terms that we really don't need. Then we have dedicated set and reset and dedicated output enables. Then per macrocell, we've got product terms A, B, and C, very inventive naming. So product term A is one of several legal sources for set reset. There's also the control term set and reset can be used instead if you want. There's product term B, which is one of several possible sources for the IO buffer output enable. And then product term C, which can be used for a couple of things. If you've got a clock enable, it's used as a clock enable. If you want a per macrocell clock for just one flip-flop that you're clocking off one weird clock that nothing else is clocked by, you can use that. And it also drives an XOR gate. So it turns out that this isn't quite a conventional CPLD structure. The output of the PLA is XORed with product term C or its complement, or a constant 1 or constant 0. This is a Xilinx proprietary optimization that is, again, documented in the datasheet, but they don't tell you how to configure in the bitstream. The intention here is to allow you to do efficient adders. You've got XORs. You don't have to do not X or Y, or not X and Y, or not Y and X. So you can just use the XOR gate. So the question is, okay, we've got 56 product terms. Which one is PTC? No idea. Well, it turns out we can configure the PLA as much as you want. We already know how to configure that. We've reversed all the bits for that. We can configure the global routing as much as you want. And it's fairly easy to generate a bit stream that is known to use product term C from the tools. All we have to do is either synthesize something with an XOR in it, or it turns out there's actually an optimization of the tools. If you are not using the OR array, so say we just have y equals A and B. It turns out that if we set the AND array to, if we set the OR array to output a constant 0, and then we XOR that with product term C, we no longer have the OR array in our critical path. So you can shave about 500 picoseconds off the propagation delay by doing this. The compiler, trying to optimize speed, does this by default if you're not using the OR array. So therefore, just by creating an equation like y equals x in your source code, you can trivially produce a bit stream that uses product term C. So all we have to do is say, okay, let's make something that uses product term C. We'll spam these black box macrocell bits into all of the outputs and just start feeding inputs into various product terms until we find one that hits. Well, it turns out it is zero-based term 3n plus 10. Unfortunately, I have things called customers that kept me from working on this project as much as I would like, so I never actually figured out what product terms A and B are. I'm pretty sure that they're either just above or just below product term C. I don't know which. The control terms, if you remember, product term C is 3n plus 10. So below number 10, none of these terms are actually being used for anything in PTABC. So the control terms are probably among the first couple of terms. But again, I have not actually had time to figure out which is which. One more wrinkle is that there are some global configuration bits. So if you remember, we've got the structure of the die on the left side and the right side. We've got the function blocks. On the top, we've got global routing. On the bottom, we've got global routing. So that pretty much makes a big donut shape. In the middle of that, there's wasted space. But no, it's not actually wasted. There's 22 single configuration bits in the middle of the die. We know 3 of them control the VT for the I/O banks. The device has 2 I/O banks, but the original XC2C32 only had 1 I/O bank. So they did a clever hack. They are now bitstream compatible with the 2C32. They added 4 more configuration bits. So the way they did this is they have 1 global bit. If this bit is set, then it'll use the old school XC2C32 configuration setting for this. The newer ones are 2 additional per bank bits. So it actually just does a bitwise AND between the global bit and the per bank bit. If you erase the device and you don't program these last couple of fuses, then you will get the default XC2C32 behavior, in which you've got 1 I/O standard for everything. If you're compiling for the 32A, now you set that other bit as a constant 1, leave the other one set the way you want, and now you get the ability to set VT for each bank independently. So it's actually pretty clever. Then there are other miscellaneous things that are there. The comments in the bitstream were a little bit helpful for this. So I know there's 3 bits that configure global clocking, 2 bits that configure global set reset, 8 that configure global output enable. I do not actually know what the coding for these bits are at this point, so there's still some work in progress going on. Now I will get to the actual toolchain that I'm producing. I've called it Libcrowbar after the Flying Crowbar project on Silicon Prawn. The goal is to, in general, produce open source tools for programmable logic. It does need a lot of refactoring and tweaking. It does not do nearly everything that I want. It only supports the 2C32A right now. We can scale to other devices. The 64-cell device is pretty much just a scale-up of the 32. I've decapped it. I've looked at the top layer. It's just a 2x2 grid of function blocks instead of 1x2. The ROM for the routing fabric will have to be decoded separately, but that shouldn't take too long. The ordering of the bits will have to be decoded, but again, that shouldn't take too long. I can probably just brute force it. And the macrocell configuration and everything else is pretty much exactly the same. The larger devices, the 128, 256, 384, and 512, add some additional features to macrocell. So in addition to figuring out the extra routing stuff, I will actually have to do some additional reversing of the macrocell logic. So that remains a work in progress, but that is a goal. The library is BSD licensed. You can grab the code from there. I do not recommend attempting to use it in its current state. It's more of something to look at and understand how the chip works, and maybe in a couple of months, they will have something that's actually stable enough you can actually use. But I do have a quick usage example here. So we have a bunch of I/O pins. We select P8, P6, P38, P37, whatever. Then we get the IOBs for each of these. We can now select the I/O standards, some output enables. We're not going to use termination. We're not going to use Schmidt trigger. These are all bits in the macrocell that I was able to figure out. There are still quite a few related to clocking that remain unknown at this point. And then there's quite a bit more going on below this. I can pull up full source if anybody's interested in looking at it. But the end result is that I can go from an in-memory technology mapped netlist created like this as C++ objects. I can then place and route this, produce a valid bit stream, flash the device, and have it work. I can also go the other way around. I can go from a program device, I can read out the bit stream. I can turn it into an ASCII art schematic, and I can turn it into synthesizable Verilog, as long as you're not using the features I haven't yet reversed the functionality of. The remaining thing in the forward tool chain is I would like to integrate with Yosis for synthesis, take the output of Yosis, do technology mapping on that, and then feed it into Libcrowbar. At that point, I will have a full Verilog 2-bit stream toolchain. I'm not quite there yet, but it's coming close. The other tool I've made, if any of you have used Plan Ahead from Xilinx, I called mine very inventively FC Plan for the Flying Crowbar floor planner. So it is a floor planner and physical layout viewer. I currently only have rendering for the AND array and the global routing. The OR array, I do have the functionality reversed. I have not written the code to actually draw it, but I can actually open up a bit stream and look at the individual settings in the AND OR array. The Macrocells also, I've reversed some of the bits, not all of them, but I have not yet written code to actually render the appearance of them as, checkboxes for, okay, this Schmidt trigger is enabled, the terminator is enabled, the slew is fast or slow, and so on. So those all remain on the wish list at this point. The configuration bits are known. You can access them from Libcrowbar. You cannot do so in the GUI. So here's one more view of FC Plan. This is showing, as you zoom out, the product terms shrink down to smaller columns. You can see the full global routing matrix here. This is the actual VIA pattern. It doesn't show up as well on the projector, again, as I would have liked. But you can see the actual MUX bits in there. When you zoom in the tool, you can actually see the signals coming in from the global routing, going out through these vias and into the AND and OR arrays. Before we get to the demo, I do want to thank John McMaster from Silicon Prawn. Hi, John. He did most of the large-scale optical imagery for this. He also did the dash etching, which was very helpful. Then Ray Dove and Brian Colwell at RPI run the material science lab and the clean room, respectively. They were quite helpful when it came time to getting access to the electron microscope and the clean room and so on. As far as I know, I am the only computer science student there who ever ran the electron microscopes. But I did actually get access to the clean room, the SEM, the FIB. I was trained on all of them, and they were quite helpful. And then the Silicon Prawn team in general was quite handy when it came to just getting feedback and sanity checking, and does this look okay to you? Or I can't quite make out what this connects to. Do you have any ideas? Or just sharing process suggestions. Okay, what are some ways I can get this etch to be a little more even? Something like that. So now, time to tempt the demo gods. So I have my JTAG daemon connected already. This is my dev board. It has a small FTI 232 on there that I'm using for JTAG. And so what I'm going to do is I'm going to create a bit stream using Libcrowbar that will act as a NOT gate and a buffer. And then I'm going to bit bang inputs going into there with the FTDI chip. And we should see one LED and then the other alternately lighting up. I don't know if you guys can see. Right up here, these LEDs are blinking back and forth. So if we scroll through the output here of the tool, you can see we start out initializing, we connect to the JTAG chain, we see, okay, there is a device. One odd note, the Cool Runners are the only devices I've ever actually looked at in which the JTAG device ID actually includes the package as well as the device. So what this means is that they've actually got a fuse somewhere in the die that says, oh, this is a TQFP, this is a BGA. I've never seen that on any other device. Every other FPGA or microcontroller or anything I've used, the device ID was the same between different packages. Anyway, so we confirm, okay, yes, the FTDI chip has GPIOs on it. We generate our net list. We figure out the actual function block and macrocell locations of the I/O buffers we're using. Then it runs the fitter through I/O banks, macrocells, function blocks, does global routing, repeats for the other function block, does global routing for that, confirms, okay, fitting is complete. Took 620 microseconds. If any of you have used the Xilinx compilers, they're not that fast. Then we finished generating the bit stream. That's kind of slow right now. It took a couple of milliseconds. I'm pretty sure I can optimize this. Mind you, this is a debug build with profiling turned on, so it'll be a lot faster if I actually compile with optimizations. Then we actually configure the device. We verify, okay, yes, we are talking to the right device. We've got the right number of fuses. We erase it. We make sure it's blank. And then we just bit bang the out as 0 and 1, and it confirms that the loopback going back to the FTDI chip does have the values we expect. One of them is X, one of them is X prime. So that looks good. Now let's see what happens if we actually want to reverse this. Let me see if I can up the font size. Can people read this? I'm guessing no. That better? All right. So this is what happens when we actually try dumping the bitstream. This is not the same bitstream. This is a different one. I just picked at random I had sitting around. So we have a nice ASCII art schematic showing all the inputs coming in from the PLA, or coming in from the global routing. Each of these represents one connection. That's one configuration, but it's actually connected to something. We have the X and the X bar outputs. Nice big grid. Then 56 product terms to the OR array. We've got outputs going to the Macrocell array. This table looks a lot nicer at 1080p when your font isn't quite so big. But I do actually have details on, okay, this output is floating. This one is configured as an input. This is an input. This is an input. There's an output in here somewhere, probably on the other one. Whatever, I must have scrolled past it. So now on the output, we have the I/O standards. It turns out even though there's about a dozen I/O standards you can pick from its synthesis time, in the bitstream there's only two. There's the high voltage and the low voltage. So there's 1.8 and 1.5, and there's high voltage. So my guess is what this does internally. I have not fully reverse engineered all of the I/O driver circuitry, but what I'm pretty sure it does is it selects a single threshold or another, and then thicker or thinner gate oxide in the output. There's about 4 or 5 different sets of drivers in the output for fast and slow, different voltages, and so on. I haven't actually done TEM cross-sections and measured VTV's transistor or anything like that. It wasn't necessary for this. And then we've got a bunch of stuff here for the global clock muxes, global set reset muxes, and everything, and all this remains unknown. I know roughly, I know which bits these are. I don't know what the functionality of those bits is. And then, let's get to the fun part. Let me actually switch to the adder test.ged file. This one has a simpler, this is a 4-bit adder, which will make a lot more sense than the 32-bit adder I was showing in the other one. So, here's our RTL. It is pretty much the assembly language of Verilog. This is a direct analog of the actual PLA structure. I have not attempted to figure out any higher level structure. This is electrically equivalent. I have not tested synthesizing it. I actually just found a bug last night here on lock equals that should be quoted. So right now the output as formatted won't synthesize, but it would be fairly trivial to fix that and make it actually synthesize and work. And then I've got function block 2. There's not really anything in there. So now before we get to the questions, I'm just going to jump up to FC Plan and show you guys what the actual structure looks like in the floor planner. Guess I found a bug. The scroll on this thing is really sensitive. All right, can I go just one click in? All right, that's probably good enough. So you can see what we've got. Initially, we're bypassing all the inputs, so we're not using the first couple rows coming off the global routing. Then down here, I've got one signal coming in. It's hooked up over here to X. It's hooked over here to X prime, goes into the AND gate. Then we go down there and so on. So we do actually have a full physical layout viewer at this point. So now I'm just going to jump back to the slides for just 1 or 2 more before we get back to... So what remains as far as future work? We still have to figure out the last of the special product terms. There still are about 6 or 8 bits in each macrocell that we have not yet figured out the functionality of. There's still some more in the global devices, the global bits. And as I did mention, there is a little bit more I need to do to support larger devices. As far as the tool chain, I want to do more work in the decompiler. My long-term goal with this work is to integrate with some other bitstream reversing projects and so on and create the IDA for hardware. I would like to be able to go from bitstreams for Cool Runner, bitstreams for Spartan 6, bitstreams for Stratix 4 and everything, and go from that up to a device-mapped, device-dependent technology map netlist, abstract that up to a device-independent netlist, something more along the lines of LLVM IR for hardware, and then do higher-level analysis on that. Figure out, okay, this combination of XOR gates and muxes looks like a 32-bit adder. This combination of stuff looks like a 10-to-1 mux. This combination of stuff looks like a Cortex M3. I would like to eventually be able to have something along the lines of FLIRT here. I do know that subgraph isomorphism is NP-complete. I don't know if I can make a randomized or approximated algorithm that's fast enough. That remains a topic for future work, but it is on the wish list, whether it is physically possible or not. So at this point, I'll take questions. Seeing none, I guess we're done. Thank you.